Why would the United States military spend 4 agonizing weeks relentlessly bombing their own multi-billion-dollar supercarrier? In the spring of 2005, a massive warship was towed out into the deep Atlantic, not to fight an enemy, but to face a classified execution ordered by its own creators. This is the heartbreaking final chapter of the USS America, a legendary vessel that served her country for decades, only to be systematically blasted apart by the very navy she protected. For weeks, the ocean echoed with the sound of explosions ripping through her loyal metal frame. Behind closed doors, the Pentagon authorized a highly classified test that they desperately wanted to keep hidden from public eyes. Sinking a modern supercarrier was considered an impossible task, yet the military needed to know exactly what it would take to destroy their own crown jewel. In 2005, the Navy towed this 84,000-ton behemoth into deep waters. They unleashed torpedoes, cruise missiles, and internal explosives directly at it. This wasn't a mistake, it was a calculated scientific execution to harvest the secrets of warship survival. Welcome to weapons science. To understand why this happened, we must first look at the legacy of the USS America, designated CV-66. Commissioned in 1965, she was a Kitty Hawk-class supercarrier built during the height of the Cold War, designed to project absolute American dominance across the global oceans. For over 30 years, CV-66 patrolled the tensest waters on Earth. From the Gulf of Tonkin during the Vietnam War to the fiery skies of Operation Desert Storm, she was a floating fortress that launched thousands of combat sorties, earning her place in the annals of naval history. But by 1996, the relentless march of technological progress had caught up with her. Newer nuclear-powered Nimitz-class carriers were taking over the fleet. The USS America, running on conventional steam turbines, was decommissioned and left to rust in the mothball fleet. Usually, retired carriers face one of two fates. They are either preserved as floating museums for future generations to admire, or they are sold to shipbreakers to be chopped up into scrap metal. But the Pentagon had a far more radical, classified plan for CV-66. The Navy realized that they possessed a unique asset. They had an intact, modern supercarrier hull that was no longer needed for active duty. Instead of letting her fade away quietly, they decided to turn her into the ultimate target for a highly secret SYNCEX operation. SYNCEX, or sinking exercise, is a standard military program designed to test weapons against real hulls. But never before had the United States attempted to sink a vessel as massive as a supercarrier. The sheer scale of the trial was unprecedented in modern naval warfare. The decision sparked intense outrage among veterans who had served aboard her. They argued that the legendary ship deserved a peaceful retirement as a museum, not to be blown apart and sent to the bottom of the ocean like a piece of common marine trash. Protests were organized and petitions were sent to the Pentagon, pleading for the ship to be saved. But the Navy remained firm. The scientific data that could be gathered from destroying the USS America was simply too valuable to ignore, especially with new threats emerging. With rising geopolitical tensions and the development of advanced anti-ship missiles by rival nations, the U.S. Navy desperately needed to know if their floating air bases could survive a direct hit. The fate of CV-66 was sealed. She would die so that others might live. This was not an act of disrespect, but the ultimate sacrifice. The USS America was going to serve her country one last time, acting as a massive real-world laboratory to test the absolute limits of naval engineering under the most extreme conditions imaginable. As the towing cables tightened and the ship began her final voyage out to sea, engineers and military scientists prepared their instruments. They were about to conduct the most detailed, violent, and expensive structural test in the history of the modern world. You might wonder, in the age of supercomputers and advanced physics software, why didn't the Navy just simulate the destruction? Why waste a multi-billion-dollar hull when you can run 1,000,000 virtual tests at a fraction of the cost? The answer lies in the limits of code. While modern computer models are incredibly sophisticated, they are ultimately limited by the assumptions programmed into them. A supercarrier is an unbelievably complex labyrinth of over 60,000 tons of structural steel, miles of pipes, and thousands of watertight compartments. When a high-explosive warhead detonates inside a warship, the resulting physics are chaotic and unpredictable. The shockwaves bounce off bulkheads, deform steel plates, rupture fuel lines, and create complex gas expansions that no supercomputer on Earth can fully model. Simulations often fail to capture the secondary and tertiary effects of a strike. For instance, how does the vibration of a torpedo blast affect sensitive electronic systems 3 decks above? Or how does a fire spread through damaged, deformed cable trays? To build truly survivable ships, naval architects need hard empirical data. They need to measure the exact pressure waves, the precise deformation of steel, and the actual performance of watertight seals when subjected to real, unsimulated combat damage. This empirical data is the foundation of naval architecture. Without it, designers are essentially guessing, which could lead to catastrophic design flaws that are only discovered when a ship is hit by an enemy missile during an actual conflict. The Navy also needed to evaluate the effectiveness of their active damage control systems. How do automated fire suppression systems, bilge pumps, and emergency structural shoring perform when the entire ship is shaking from continuous, heavy bombardment? Furthermore, a physical test allows engineers to validate and calibrate their computer models. By comparing the actual damage on the USS America to their pre-test simulations, they could drastically improve the accuracy of their software for future ship designs. In the cold logic of military planning, sacrificing one retired carrier to acquire this priceless dataset was an easy decision. It was an investment that would safeguard the lives of thousands of future sailors and protect trillions of dollars in naval assets. The USS America was chosen because its structural design, though older, shared the same fundamental DNA as the modern Nimitz class and the then conceptual Gerald R. Ford class carriers. The lessons learned here would directly translate to the modern fleet. With the justification finalized, the project was greenlit under strict secrecy. The Navy began the monumental task of preparing a massive, toxic, and complex supercarrier for its final, self-inflicted destruction far out in the deep waters of the Atlantic. Preparing a supercarrier for a syncax is not as simple as towing it out and shooting at it. It is a highly regulated, environmentally sensitive, and technically demanding process that took months of intense preparation at the Philadelphia Naval Shipyard. The first and most critical step was environmental decontamination. An aircraft carrier is a floating city containing vast amounts of hazardous materials, including asbestos, polychlorinated biphenyls or PCBs, and thousands of gallons of residual fuel and toxic lubricants. Every single drop of fuel, oil, and hydraulic fluid had to be meticulously drained from the ship's massive tanks and miles of complex piping. Environmental protection laws required that the ship be as clean as possible before being allowed to sink to the ocean floor. This was a massive undertaking. Teams worked around the clock, flushing tanks, removing electrical transformers containing PCBs, and stripping out miles of wiring insulation. The goal was to leave nothing but clean, inert steel and non-toxic materials behind. Once the environmental cleanup was complete, the engineering teams moved in. Their job was to transform the USS America into a giant floating laboratory. They installed hundreds of highly sensitive sensors, cameras, and data recording devices throughout the ship. These sensors were designed to measure structural strain, shockwave pressure, thermal heat, and flooding rates. Because the ship would eventually sink, all this valuable data had to be transmitted in real time via telemetry to nearby monitoring vessels. To ensure the survival of the recording equipment during the violent explosions, the main data hubs were encased in heavily armored, shock-isolated containers. These black boxes were designed to withstand extreme forces and remain functional until the very end. The Navy also strategically placed internal video cameras protected by thick, blast-resistant glass housings. These cameras would provide scientists with a first-hand view of how bulkheads buckled and how water rushed into the compartments during the attacks. In addition to active sensors, the engineers placed structural targets inside the ship. They wanted to see how different types of armor plating, welds, and structural joints would hold up against the devastating force of modern military-grade explosives. Finally, the ship's watertight doors were configured in specific patterns. Some were welded shut to simulate a perfectly sealed warship, while others were left open to test how flooding would progress if crew members failed to secure their stations in time. On the 19th of April 2005, the fully prepared, instrument-laden hull of the USS America was towed out of Philadelphia. She was headed to a designated deep-water target area approximately 400 miles off the coast of Virginia, where her final trial would commence. The bombardment of the USS America began in late April 2005. The Navy designed a highly structured, multi-phase assault plan to test the ship against a wide variety of threats, starting with simulated near misses and progressing to direct, devastating impacts. The first phase involved air-delivered ordnance. Navy fighter jets flew high above, dropping laser-guided bombs and launching anti-ship missiles directly at the carrier's massive flight deck and island superstructure to test the durability of her upper armor. The explosions were colossal. Fireballs erupted on the flight deck, sending jagged metal shrapnel flying hundreds of feet into the air. Yet, to the amazement of the observers, the massive steel deck, designed to support heavy aircraft, absorbed the impacts with minimal structural failure. Next came the surface-launched weapons. Destroyers and cruisers fired cruise missiles from miles away. These weapons, traveling at near supersonic speeds, slammed into the side of the carrier's hull, testing her side armor and internal blast deflection systems. The impact tore gaping holes in the outer hull plates, but the carrier's internal compartmentalization proved to be incredibly effective. The blast energy was channeled outward and upward, preventing catastrophic damage to the critical inner core of the ship. Then, the Navy unleashed the most feared weapon in naval warfare, the heavyweight torpedo. Launched from an attack submarine lurking deep below, these weapons were designed to detonate directly underneath the carrier's keel, where there is no armor. An underwater explosion is uniquely destructive. When a torpedo detonates beneath a ship, it creates a massive gas bubble that lifts the vessel out of the water, followed by a sudden collapse that drops the ship, effectively breaking its back under its own immense weight. The torpedo blast sent a massive plume of water high into the air, shaking the entire 84,000-ton hull. Yet the USS America refused to sink. Her heavy keel and robust structural framing absorbed the immense stress, proving the resilience of her Cold War-era engineering. To push the ship to her absolute limits, the Navy also detonated internal explosives. They placed shaped charges inside critical compartments, simulating the effects of a weapon that had successfully penetrated deep into the interior before exploding. These internal blasts ruptured bulkheads and caused localized flooding, but the ship's design, featuring hundreds of independent watertight cells, successfully contained the water. The flooding was isolated, preventing a chain reaction that could lead to a rapid capsizing. Day after day, week after week, the onslaught continued. The USS America was battered, scorched, and scarred, yet she remained stubbornly afloat. The sheer durability of the supercarrier was stunning even the most experienced naval engineers on the observation ships. How did the USS America survive a 4-week bombardment that would have easily sent a dozen standard destroyers to the bottom? To understand this, we must dive into the fascinating physics of aircraft carrier design, starting with the concept of reserve buoyancy. Buoyancy is the upward force that keeps a ship afloat, equal to the weight of the water the ship displaces. Because a supercarrier is so incredibly massive, it displaces a gargantuan volume of water, giving it an immense amount of reserve buoyancy to spare. But the real secret to her survival is extreme compartmentalization. The interior of the USS America is not a wide-open space. It is divided into more than 2,000 independent, watertight compartments. It is essentially a giant metal honeycomb. If a weapon ruptures the outer hull and floods a compartment, that flooding is confined to that single small space. Even if dozens of these compartments are completely filled with seawater, the ship still has more than enough reserve buoyancy to remain afloat. Another critical design feature is the double hull. Modern supercarriers do not have a single layer of steel separating them from the ocean. Instead, they feature an outer hull and an inner hull separated by several feet of void space or fuel tanks. When a missile or torpedo strikes the ship, the explosion must first penetrate the outer hull, travel through the void space, which absorbs and dissipates a massive amount of the blast energy before it can even begin to threaten the inner hull. These void spaces are often filled with water or fuel, which acts as an incredibly effective liquid shield. The density of the liquid absorbs the high-speed fragments and shockwaves from an explosion far better than empty air or solid steel alone ever could. Furthermore, the structural steel used to build these warships is of an incredibly high grade. High 80 and HY100 steel alloys are designed to be extremely tough yet ductile, meaning they can bend and deform under immense pressure without cracking or tearing apart. This ductility is crucial. In an explosion, a rigid hull would shatter like glass, leading to widespread flooding. A ductile hull, however, warps and dents, absorbing the energy of the blast while maintaining its watertight integrity and keeping the ocean out. To make things even more difficult for any potential attacker, a supercarrier is designed with a high level of stability. Its wide beam and low center of gravity mean that even if it takes on thousands of tons of water on one side, it is extremely difficult to capsize. All of these passive design features work together to create an incredibly resilient platform. The USS America was demonstrating to the world that a modern supercarrier is not just a soft target, it is a virtually unsinkable mountain of steel. As the weeks of bombardment drew to a close, the sensors on the USS America had gathered a treasure trove of invaluable, highly classified data. This information was immediately transmitted to the Navy's premier research and design centers. The primary recipient of this data was the design team working on the next generation of American supercarriers, the Gerald R. Ford class. At the time, the Ford class was still on the drawing board, and the lessons from the USS America would shape its very foundation. One of the key findings was how shock waves traveled through the hull. Engineers discovered that certain critical electronic systems and weapon elevators were highly vulnerable to the vibrations caused by near-miss explosions, even if the hull itself was undamaged. To fix this, the Gerald R. Ford class was designed with advanced shock isolation mounts for all critical systems. These specialized rubber and steel mounts act as heavy-duty shock absorbers, decoupling sensitive gear from the ship's vibrating steel skeleton. The data also led to significant changes in the ship's internal armor layout. Engineers identified specific areas where the blast deflection bulkheads could be reinforced with newer, lighter composite materials, offering superior protection without adding unnecessary weight. Furthermore, the USS America Synkex validated the use of electromagnetic aircraft launch systems, or EMALS, over traditional steam catapults. The test showed that steam piping systems were highly vulnerable to rupturing under heavy shock, creating a severe hazard. By replacing steam pipes with electrical cables, the Ford class eliminated a major vulnerability, making the ship significantly safer and more resilient in a combat environment. This was a direct revolutionary improvement born from the destruction of CV-66. The test also provided invaluable training data for Navy damage control teams. By studying the real-world progression of fires and flooding, the Navy was able to completely rewrite their emergency response manuals and develop far more effective firefighting tactics. They developed new rapid response shoring techniques and automated systems that can isolate flooded compartments in a fraction of the time. The survival rate of a modern carrier crew was dramatically increased because of the sacrifice of this one ship. The wealth of information gathered during those 4 weeks was so extensive that it is still being studied by naval architects today. It remains one of the most significant and closely guarded secrets in the entire arsenal of the United States military. The USS America had proven her worth beyond measure. She had withstood a beating that no other ship class on Earth could have survived, and in doing so, she ensured that the next generation of American supercarriers would be the most survivable warships ever built. By mid-May 2005, the scientific objectives of the Synkex had been fully accomplished. The USS America was heavily damaged, her hull scarred and black, but she still refused to sink on her own. It was time for the final deliberate blow to bring the beast down. Because conventional weapons had failed to breach her structural integrity enough to sink her, the demolition team had to board the carrier one last time. They placed massive, specialized scuttling charges deep within the lower engineering spaces, right against the ship's double bottom. These scuttling charges were designed to tear massive holes in the very bottom of the hull, allowing water to rush into the largest compartment simultaneously, overcoming the ship's remaining reserve buoyancy in a rapid, controlled manner. On the 14th of May 2005, the order was given. The scuttling charges were detonated. A series of deep, muffled rumbles vibrated through the water as the explosives tore through the keel. The final, irreversible flooding of the USS America had begun. The massive ship began to settle deeper into the Atlantic. Her stern dipped first, the water slowly creeping up the flight deck. It was a silent, solemn spectacle. On the nearby observation ship, sailors and officers stood at attention, saluting their fallen sister. With a final majestic tilt, the bow of the USS America pointed toward the heavens. The water rushed over her flight deck, swallowing the island's superstructure, and with a great hiss of escaping air, the legendary supercarrier slipped beneath the waves for the very last time. She descended nearly 17,000 feet to the bottom of the ocean, landing upright on the abyssal plain. There, in the silent, pitch-black depths of the Atlantic, she rests today, a permanent monument to the incredible power and resilience of American naval engineering. The ultimate takeaway from this historic test is clear. A modern U.S. supercarrier is virtually unsinkable by standard conventional weapons. It took 4 weeks of continuous, uncontested bombardment and deliberate internal demolition to finally send her to the bottom. The sacrifice of the USS America ensured that the sailors of today and tomorrow sail on the safest, most survivable warships ever constructed. If you found this deep dive into military science fascinating, please hit that subscribe button to join us for more weapon science. Don't forget to like this video to help the algorithm share this history with others, and comment below. Do you think modern hypersonic missiles change the equation of carrier survivability? I'm Ethan Walker, and we'll see you next time on Weapon Science.